Hello friends, welcome to my lecture on formulation of partial differential equations. Let us define what do we mean by a partial differential equation first. An equation which involves partial derivatives of an unknown function of two or more independent variables is called a partial differential equation. These equations arise in connection with various physical and geometric problems. The independent variables may be time and one or several coordinates in space. We shall see later on an example of a physical problem and see how the partial differential equation arises there. The order and degree of a partial differential equation are defined as the order of the highest derivative that occurs in the differential equation is called the order of the partial differential equation, and the degree of the highest order derivative is defined as the degree of the partial differential equation. A partial differential equation is defined as linear, just as in the case of an ordinary differential equation if the dependent variable and the partial derivatives they occur in the first degree and separately. So, in the partial differential equation the dependent variable and partial derivatives should be of first degree and they should not occur as products. If such a thing is not true, okay, then the partial differential equation will be called as non-linear. Now, we define a homogeneous partial differential equation. If each term of a partial differential equation contains either the dependent variable or one of its derivatives, the equation is called as a homogeneous differential equation, otherwise we shall call it as a non-homogeneous equation. For example, let us look at the example of a one-dimensional wave equation. This is delta square u by delta t square c square delta square u by delta x square. This one-dimensional wave equation, we can see that this is second order differential equation because second order derivative is the highest order derivative here. Moreover, the second order derivatives are of power 1, their degree is 1. So, it is second order with first degree and moreover each term of the differential equation contains the derivative and therefore it is a homogeneous differential equation. So, it is second order first degree linear differential equation which is homogeneous. Here let us take another example, one dimensional heat equation. Here this is again second order differential equation because we have second order derivative here which is the highest order derivative and its power is 1. So, it is second order first degree, moreover each term is containing the derivative. So, it is homogeneous equation and also it is linear because the independent variable u and its derivatives they occur in first degree and they are occurring separately. So, it is second order first degree linear homogeneous equation, and this is second order two dimensional Laplace equation. This is again second order linear differential equation which is of first degree, it is homogeneous and it is linear. Let us consider two dimensional Poisson equation. So, this is again second order linear, second order first degree linear non-homogeneous equation if fxy is not equal to 0. If fxy is equal to 0 for all xy in some region, then it will also become a homogeneous equation, and this is a three dimensional Laplace equation. So, here this is second order first degree homogeneous linear differential equation. Now, so t in these examples t is the time and x, y, z are Cartesian coordinates, and as I said fxy if it is non-zero, then in the example 4 then we have a non-homogeneous second order first degree linear partial differential equation, while the other equations are second order first degree homogeneous linear partial differential equations. Okay, now solution of a partial differential equation. A solution of a partial differential equation in a region R of the space of independent variables is a function which has all the partial derivatives that occur in the partial differential equation and satisfies the differential equation at every point in R. In general, a partial differential equation may have a large number of entirely different solutions. For example, if you look at the example 3, this one delta square u by delta x square plus delta square u by delta y square, two dimensional Laplace equation, then we can verify that x square minus y square, let us see x, suppose delta square u by delta x square plus delta square u by delta y square. Let us consider the case of this Laplace equation. Then if you take u equal to x square minus y square, we can verify that u equal to x square minus y square is a solution of this Laplace equation, because if you take the first order, find the first order partial derivatives here, then they are 2x and minus 2y, and when you find the second order partial derivatives, they come out to be 2 and minus 2, and so which implies that this is equal to 0. So, u equal to x square minus y square is a solution of this. Similarly, we can see that if u is equal to e to the power x sin y, then ux, or you can say delta u by delta x, is e to the power x sin by uxx while uy so delta square u by delta y square is minus ex sin y. So, delta square u by delta x square plus delta square u by delta y square is equal to 0. And so, u equal to e to power x sin y is also a solution of this Laplace equation. Similarly, you can verify that u equal to ln x square plus y square also satisfies the Laplace equation. So, and these solutions are entirely different in the sense that there is a polynomial in x and y, while it involves exponential and trigonometric functions, and this involves a logarithmic function. So, they are entirely different from one another. So, we have a large number of entirely different solutions of this differential equation. Now, so one can then see how we can obtain a unique solution of a partial differential equation. The unique solution of a partial differential equation corresponding to a physical problem is obtained by using the initial and boundary conditions which arise from the physical situation. In some problems you will see that the values of the required solution, they are given on the boundary of some domain, which are called boundary conditions, while in some cases when t is one of the independent variables, the values of the required solution at t equal to 0 will be given, and they are called as the initial conditions. So, using those initial and boundary conditions, we arrive at a unique solution of the partial differential equation corresponding to a physical problem. Now, like we have seen that in the case of ordinary differential equations, we have the superposition principle, that is, if y1, y2, yn are n independent solutions of the homogeneous linear differential equation, then c1 by 1 plus c2 by 2 plus cn by n is also a solution of that. So, here also we have the superposition principle. This theorem 1, if u1, u2, un are any solution of a linear homogeneous partial differential equation in some region, then c1 u1 plus c2 u2 plus cn un, where c1 c2 cn are any constants, is also a solution of that equation in that region. So, this you can easily verify by picking up any homogeneous linear partial differential equation, it can be easily seen. Now, we shall be discussing in our lectures solutions of some special types of partial differential equations, and so for brevity we shall be assuming that the partial derivative of z with respect to x is denoted by p, partial derivative of z with respect to y is denoted by q. So, first order partial derivatives with respect to x and y are denoted by p and q, and second order partial derivatives, that is zxx is r, zx by is s, and z by is denoted by t. Now, we are going to see how the partial differential equations arise as a result of eliminating arbitrary constants and arbitrary functions. So, suppose we have a relation in x by z and a b, where a b are arbitrary constants. So, let us see derivation of a partial differential equation as a result of eliminating arbitrary constants. So, let us say we are given a relation f x y z a b equal to 0, where a and b are arbitrary constants. So, then taking x and y as the independent variables, we shall be getting the following: taking x and y as the independent variables, on differentiating this equation 1, on differentiating 1 with respect to x, we get delta f by delta x plus delta f by delta z into delta z by delta x equal to 0, or by the notation that p equal to delta z by delta x, we have this equation equal to 0, and by differentiating 1 with respect to y, we get r so we get two more equations. Okay. So, in order, thus we have three equations 1, 2, 3. From these three equations, in general the two constants a and b can be eliminated, and then we get, so by eliminating a and b from 1 to 3, we obtain a relation between f x by z p q equal to 0, which is a first order linear first order differential equation, that is linear in p and q. So, which is the first order equation. So, whenever we eliminate two arbitrary constants occurring in the relation, it leads us to a first order equation. So, for example, suppose z is equal to ax plus by plus ab. So, this will give you p equal to a and q equal to b. When you differentiate this equation with respect to x, we get delta z by delta x equal to a, which is p equal to a, and delta z by delta y equal to b, which gives us q equal to b. So, we get two more equations, p equal to a, q equal to b. Now, eliminate a and b from these three equations. So, then we get z equal to px plus qy plus pq, which is a first order differential equation. First order partial differential equation. Now, if you take, say for example, another example, ax square plus by square plus z square equal to 1. Here also there are two arbitrary constants a and b. So let us find the differential equation from here. So 2 we differentiated with respect to x, so 2ax plus 2z into p equal to 0, 2by plus 2z into q equal to 0. When we differentiate this with respect to x, we arrive at 2ax plus 2zp equal to 0, and when we differentiate it with respect to y, we get 2by plus 2zq equal to 0. So we get r ax plus z into p equal to 0 and by plus z into q equal to 0. Okay, so we get here the value of a equal to minus zp divided by x, and this will give you the value of b equal to minus zq divided by y. So let us substitute these values of a and b in the given equation. So we have thus minus zp upon x into x square plus minus zq upon y into y square plus z square equal to 1, or we shall have minus zpx minus zqy plus z square equal to 1. Okay, or we can write it as zpx, z times px plus qy equal to z square minus 1. Okay, so this is the first order differential equation that we get after eliminating the two arbitrary constants a and b. Okay, now let us let us derive a partial differential equation by eliminating arbitrary functions. So we derivation of a partial differential equation as a result of eliminating arbitrary functions. So let us consider that u and b are two known functions of x and y and z. Let us consider that u comma b are two known functions of x, y and z, and further there is a relation phi v equal to 0, where phi is an arbitrary function. So let us derive the partial differential equation from this relation phi u b equal to 0. So differentiating equation 1 with respect to x, we get delta phi over delta u to delta u by delta x plus similarly differentiating with respect to v, we get with respect to y, we get so differentiating with respect to y the equation 1, we shall arrive at Now we eliminate the known quantities delta phi over delta u and delta phi over delta b from 2 and 3, eliminate we get this I can write as P into this I can write as Q. So, this into this plus this into this equal to 0. So, I can write it as equal to, and then I can divide. So, I will get minus sign, and minus sign will cancel. So, equality here we will get equal to okay. Yeah, so this into that, this into this. So, Vx plus Bz P into Uy plus Uz into Q, okay, which is a first order which is a first order partial differential equation, and it can be expressed in the form P into P plus Q into Q equal to R, okay, with suitable values of P, Q and R which can be obtained from here. So, it is a first order partial differential equation. So, when you take, say for example, u equal to fx minus ct plus g x plus ct, when you will eliminate the two arbitrary functions f and g here, you will arrive at a second order differential equation u equal to f x minus ct plus g x plus ct. This will lead you to second order differential equation, and similarly here when you take the third case z equal to a e to the power minus c square t cos cx, here there are two arbitrary constants a and c, you will get a differential equation z equal to a times e to the power minus c square t cos cx. So, this will give you partial derivative with respect to t as a e to the power minus c square t into minus c square cos cx, and when you differentiate z with respect to x, what you get? When you differentiate again, what you get? Okay, so if you compare this and this, okay, what you get is we arrive at this equation, okay, a c e to the power minus c square t into c square cos cx, that is delta z by delta t. So, we get so we get this second order differential equation on eliminating the arbitrary constant which occur there. Let us now go over to we are now going to see how the partial differential equation arise in a physical problem. So, let us consider the one dimensional heat equation. We shall see how we get the first order the second order differential equation delta u by delta t equal to c square delta square u by delta x square. So, let us consider the flow of heat by radiation by conduction in a uniform bar. Okay, let us consider a uniform bar, and we are so let us consider the flow of heat by conduction in a uniform bar whose sides are insulated. So, let us consider the sides of the bar to be insulated, so that there is no loss of heat by conduction or radiation from the sides. The temperature U is denoting the temperature here. The temperature U will be function of x and t. X is the distance of the point under consideration from one end, and t is the time. So, consider the element PQ of the var. Let us say OP is x, so and OQ is x plus delta x. So, let us consider the element PQ of the var of length delta x and area of cross section A. If K is the thermal conductivity of the material, then the amount of heat that flows into the element across the cross section at P in time delta T is given by minus Ka into delta U by delta x at into delta T, where delta U by delta x is the temperature gradient at the point P, and negative sign is taken because the heat is flowing in the direction of decreasing temperature. Now, similarly, the amount of heat that flows out of the element across the section at Q in time delta T will be minus Ka delta U by delta x at the point Q, which is x plus delta x into delta T. So, the amount of heat that is retained by the element PQ in time delta T will be minus Ka delta U by delta x at x minus delta U by delta x at x plus delta x into delta T. Now, due to this heat, the temperature of the element PQ will rise. Say suppose it rises by an amount delta U, then if rho is the density of the var and S is its specific heat, then the amount of heat required to raise the temperature of the element PQ by delta U is rho into A into delta x. Rho into A into delta x is the mass of the element PQ, because rho is the density, A delta x is its volume. So, rho into A into delta x is the mass into S into delta U. So, thus rho into A into delta x into S delta U is equal to minus Ka delta U by delta x at x minus delta U by delta x at x plus delta x into delta T. Now, dividing by delta x and delta T both sides, we arrive at K times this equal to rho S delta U by delta T. Now, let us take delta x and delta T to go to 0. So, when we let delta x go to 0 and delta T goes to 0, then this becomes delta square U by delta x square by the definition of limit. So, K times delta square U by delta x square becomes rho times S into delta U by delta T. So, rho into S into delta U by delta T, or we can say delta U by delta T is K by rho S into delta square U by delta x square. Since K, rho and S are constants, we can denote them by C square. We can denote K by rho S by C square. So, C square delta square U by delta x square. So, this C square is a constant and it is termed as the diffusivity of the material. So, this is how we have the differential equation of second order in the physical problem, that is the heat conduction, the flow of heat in a bar of uniform length, of uniform cross section. So, when we consider the flow of heat by conduction in a uniform bar, it results into this differential equation, delta U by delta T equal to C square delta square U by delta x square. So, this is an example of physical example where the partial differential equation occurs. With that, I would like to conclude this lecture. Thanks.